Let's understand conservative and non-conservative forces, power, and equilibrium in this video. Have you ever pushed a swing and seen it come back? Or watched a toy slow down on the floor? These simple scenes hide important ideas about energy and forces. First, imagine a block attached to a spring that keeps moving back and forth forever, with the same maximum stretch each time. In that case, the total mechanical energy, that is kinetic plus potential energy, stays the same. Now imagine the block moving, but each swing is a bit smaller until it stops. Here, the total mechanical energy is lost from the motion and appears as heat or sound. This difference helps us name two types of forces. A conservative force is one that does zero work over a closed path. So, it does not change the total mechanical energy of the system. Common examples are gravity and the ideal spring force. A non-conservative force causes mechanical energy to leave the system, like friction, air resistance, or a real rope that heats up. Even when energy leaves as heat or sound, the total energy of the universe is still conserved. Next, let us talk about power, a very useful idea in everyday life. Power measures how fast energy is used or how fast work is done in a given time. The formula is power equals work done divided by time taken, and the unit is the watt, which we say as watts. Now let us try a question together to make this clear. Question number 1 asks, a lift motor moves a fully laden lift 4 meters in 1.5 seconds, and the mass of the lift is 1,850 kilograms, ignoring friction. Part A asks for the weight of the lift. Weight equals mass times acceleration due to gravity. So, weight equals 1,850 kilograms times 10 meters per second squared, which gives 18,500 newtons. Part B asks for the upward force in the cable when the lift moves at constant speed. When speed is constant, forces balance. So the upward force equals the downward weight, that is 18,500 newtons. Part C asks for the work done by the motor. Work done equals force times distance. So work equals 18,500 newtons times 4 meters, which equals 74,000 joules. Part D asks for the minimum power of the motor to raise the lift at steady speed. Power equals work divided by time. So power equals 74,000 joules divided by 1.5 seconds, which is about 49,333 watts. That completes the worked example and shows how power links force, distance, and time. We can also write power in another way, using work equals force times displacement. So power equals force times displacement divided by time. So what do we learn from this? We learn that conservative forces keep mechanical energy inside the system. Non-conservative forces move that energy out as heat or sound, and power tells us how fast work is done. Let us quickly remember the main points. Conservative forces do zero work over a closed path. Power equals work divided by time. And equilibrium means net force is zero. For conservative forces, force equals minus the derivative of potential energy with respect to position. And equilibrium happens where that derivative is zero. Finally, equilibrium can be stable, unstable, or neutral. A ball in a bowl returns, a ball on top of a hill runs away, and a ball on flat ground stays where you put it. Keep exploring these ideas with small experiments and do not worry about mistakes. They help you learn. Thanks for watching, and feel free to explore more explanations and examples on EduRev to practice these concepts gently.